Good day. This short series of lectures is going to look at the alterations in cardiovascular physiology in health and disease. We're going to talk you through some of the cardiovascular parameters often measured as an assessment of cardiovascular physiology and how these may vary in certain health conditions and conditions of disease. And this first part, we'll be looking at normal physiology. So as usual, we'll start with a little case, a 28-year-old athlete presenting with fever and viral symptoms. He's stable. Pause the video and see if you can figure out how his cardiovascular physiology may respond to fever, dehydration, and exercise, and maybe think a little bit about how changes in ambient temperature may affect cardiovascular physiology. So when we're looking at the cardiovascular system, it's worth bearing in mind it's made up of two pumps which feed into each other. So the left heart pumps blood ultimately into the right atrium, and then the right heart pumps blood through the pulmonary circulation back into the left atrium. It's worth remembering that this is a demand-fed system. That is to say, the cardiovascular system usually doesn't just change its functioning on its own, but it does so in response to some external stimulus, such as increased metabolic demand, increased venous return, cardiac outflow obstruction, or pathological changes in contractility. And we'll be talking about all of these in the coming lectures. So throughout these lectures, we're going to talk about the following conditions and how the cardiovascular physiology changes with each. So we're going to look at exercise and fever in this lecture, and then in subsequent lectures we look at different types of shock and heart failure. For each condition, we will look at its effects on parameters concerning the left heart or systemic circulation and the right heart or pulmonary circulation. And we've listed the parameters that we're going to look at on the right of this slide. Okay, so let's look at exercise. So exercise really increases your metabolic demand, so oxygen consumption, glucose consumption, and that drives left ventricular cardiac output. However, even before the increase in metabolic rate, changes occur because of an increase in autonomic sympathetic stimulation and because of an increased venous return due to the muscular pump. So as we were saying, the initial stimulus is an increase in venous return and a decrease in venous pooling due to the muscular venous pump pushing blood, particularly from the lower limbs, back into the circulation. This increases right ventricular cardiac output and ultimately increases pulmonary blood flow. Of course, this would then lead to an increase in venous return to the left side of the heart and an increase in cardiac output, initially due to an increase in heart rate, but ultimately due to a combination of an increase in heart rate and stroke volume because of an increase in left ventricular ejection fraction. This increased cardiac output is not uniform, but is more focused on the areas with increased metabolic activity, such as skeletal muscle, and to the skin to increase heat loss from the body. Initially, the systemic overstimulation leads to an increase in systemic vascular resistance and an increase in mean arterial pressure. But ultimately, while there is an increase in mean arterial pressure, this is more due to an increase in cardiac contractility, increasing mostly the systolic blood pressure. Finally, this blood flows through the systemic circulation and back into the right atrium. However, because the right ventricle is healthy and can deal with this increase in venous return, there is no effect on central venous pressure or IVC. Okay, let's have a look at fever. So fever causes an increased metabolic demand due to the actions of vasoactive mediators and inflammatory mediators, as well as the effect of endotoxins, which lead to vasodilation, shunting, and possible cardiac suppression. These effects lead to an increase in heart rate and stroke volume, increasing cardiac output as a response to this increased demand. Vasodilation causes a decrease in systemic vascular resistance, and therefore there is an increase in pulse pressure. The systolic pressure rises because of an increase in cardiac contractility, while the diastolic pressure falls because of vasodilation. Again, there's an alteration in flow to the different organs and tissues, and in fever there is an increased flow to the splanchnic circulation, particularly the kidneys and liver, and of course to the skin to increase heat loss. This increased cardiac output ultimately feeds through to an increased right atrial venous return, and according to the amount of venous pooling, vasodilation, there may be an increase or a decrease in venous pooling. The right ventricle in a normal healthy person responds appropriately to this increase in venous return by increasing right ventricular ejection fraction, increasing heart rate, and therefore increasing right ventricular cardiac output, which means that the CVP would not really be affected. This ultimately feeds through to an increase in pulmonary blood flow, which then leads to an increase in left ventricular filling and an increase in left ventricular cardiac output. So this first lecture took us through the basic physiology of the cardiovascular system and how in health this responds to exercise and fever. If you have any questions, you can post them on the chat or you can bring them up in class. In summary, we looked at exercise and fever, and in subsequent lectures we look at different types of shock and heart failure. Thank you.